Okay. All right, morning and afternoon, everyone. Thanks again for joining and listening to the presentations today. Just give me one quick sec here. There we go. Yeah, great. So my name is Rob McEwen. I'm the co-founder with KORRAI, and today I'm going to be talking to you about some really amazing technologies. Very excited about this work that we've been putting together, which is really the culmination of some work over the years combining different types of satellite data with geotechnical hazard monitoring and using artificial intelligence to really marry all those technologies together so that we can support engineer site operators who are all tasked with making decisions on it. So quick context on me. As I mentioned, I'm the co-founder and CRO with Core AI. Long background working in mining geospatial tech, worked on our cloud native INSAR monitoring engine, combine that with convolutional neural networks, which is just a fancy collection of words for saying pattern detection using artificial intelligence. And Trail, our product today, is really what came next after those years of development and really listening to experts on the ground, which is really a system to better understand the causality and the context of credible failure modes, giving significantly more power over monitoring and surveillance data on how structures or slopes actually fail. And what I'm going to cover in the presentation today is to quickly describe some of those failure modes, which many of you already know, what satellite INSAR does well but can't do alone, and why modern agentic artificial intelligence really changes this picture in a significant way. And then quickly go through the trail system in a brief case study. And importantly, what agentic systems are not replacing, not now, and not anytime soon, in our opinion. So the premise is simple. Ground movement leaves a signature, and we can measure it from space, and we can calibrate it with sensors in the ground, but there's data everywhere. On every single slope, every piece of infrastructure across the globe, we have some kind of data. And the hard part is not just collecting the data, it's reading it together in context to figure out what the actual risk is or the changing profile of risk on these assets. And looking at slopes, every failure has its own process, its own combination of movement and rate and mechanics and trigger that are unique to geography, geology, climate, and several other forces there. Similarly, with slopes, there are also many unique processes that can define a failure on a dam. Again, still bounded by the variability of locale, but with the added parameters of the design and the expected behavior of that designed structure. The point here is that measuring movement can only be valuable really in the context of that failure mode and specifically that credible failure mode, right? Which is the process that can feasibly happen at any location. But there's no single technology that can tell you the entire story. We're often piecing together information from a partial picture with whatever information that we can get our hands on. And when things do fail, I think everyone here is pretty familiar with the magnitude of the impacts. And the important piece is that, these are not issues of the past. These are issues that we face today, and the risk is growing with the increased demand rather for energy and minerals. And the wider issue, moving beyond tailings dams to aging dam infrastructure generally is significant, but it's also compounding. We look at uh, the percentage of retiring workforce, and at least, certainly in mining and engineering roles, where this is on here, but we're seeing a 30% reduction in enrollment in some of these programs. So higher demand, we're losing a workforce, and we're losing the recharge of new professionals into that. Okay, so we talked a bit about the problem. We've talked about how things can fail. Now let's take a few moments to talk about the technologies that can help mitigate it. And one of those technologies is called INSAR. INSAR is a phenomenal technology, which, for those of you who are not familiar, it allows you to measure ground movement from space at rates as precise as millimeters or fractions of an inch. And this data is available, again, pretty much everywhere across the globe with consistent coverage over the last decade. And I'm not going to go into INSAR specifically as a technology too much. It's been around for 35 years. There's a ton of materials and presentations that are out there about this. If you're unfamiliar, I recommend you go and check out some of those or shoot me a message afterwards. I'm happy to connect in more detail. But again, just the quick synopsis is that you're getting millimeter level detection across wide areas, but the fundamental piece is that it's a partial solution when considering the mechanisms of failure modes. And in some cases, this type of technology may not even be relevant for the credible failure modes that are on site. And it's very important to match that distinction if we're going to look at a holistic monitoring plan. So if we want to be building the surveillance and interpretation infrastructure to move towards predictive capabilities, and again, we're not there yet when it comes to forecasting, um, but the synthesis of this information is fundamental. We may not be there right now, but that's the direction that things are certainly heading. And we can't map out those weak points in a process efficiently if the inputs are siloed, if the ultimate decision maker, say the engineer, the operator, can't reconcile that rapidly growing um, archive of surveillance data. And this is why we built Trail. So Trail is short for a traceable risk agent for infrastructure and logistics, which brings together satellite monitoring, field sensors, engineering reports, and construction records together in one place. And fundamentally, what it does is it provides the logic map for artificial intelligence to really stitch everything together through a system of guardrails that you can actually look at and audit and trace where results have come from. There are two fundamental components to this system. One is called a brain. So essentially that's a site ontology. So it's um, strictly defined entities and relationships between those entities. So these could be physical relationships or spatial relationships is what is the most consequential. So relationships in space and also relationships in time. And then the other component is the inference, the interface, which is a plain language retrieval, which is applying the inference on top of that data. So this allows engineers or site operators to query this ontology of data and understand those relationships. The example we'll look at here is a mine site. So if we try to represent let's say a tailing cell as a graph structure, then that tailing cell has associations with instrumentation like piezometers. It has design documentation that describes what how it was built and what specifications. It's influenced by rainfall. It has spill points. So there's all these different components that define what the structure actually is. And again, going back to how it could fail and how those data that are being collected around the site can help understand that. And the way that the system works is that we're allowed to, and the system enables the user to query against certain events. So essentially, there's five main steps to how the trail agents work. And I think the most significant or consequential really is the first three is the planning, the fetching, and the reasoning. And this is where really the sub agents are doing a lot of work. This is where they're pulling context, they're indexing it, they're forming those relationships so that when you as a user put in a question, it's correctly grabbing the information and also, again, creating that audit trail for you to reconcile those results. Um, some of the key pieces is, again, strict ontology, source linked finding, and then reasoning chain logs. So again, going back into that auditability component. So we'll quickly walk through a little bit of a case study just to see how this can work in practice. So we've looked at the Faro mine site. So the Faro mine site is a former mine, which is so essentially the operator went bankrupt and then the mine fell into federal care. It's a site that's looking at about $1 billion in remediation costs, and it's gone through several hands, has tons of data that's associated with it. And one of the examples that we're going to use specifically from Faro is to look at one of the credible failure modes. So there's a number of credible failure modes on the site, but the one that we're going to look on in particular is overtopping. So too much water goes into the system, and that dam doesn't contain it anymore, and the water spills out over top of it, contaminating the environment. So let's say that, put yourself in the shoes of someone who is actually monitoring the site and concerned about it. So let's say that, there's a significant amount of rain that's falling at the moment, and you want to understand, okay, well, how does this change my risk profile, or, the likelihood of this overtopping event occurring? So what someone could answer, or rather query the system with, is to say, okay, there's a significant rainfall event that's underway. What's the current state of evidence for overtopping risk at the dam, and how does this event compare with historical precedent? And what's happening when a user sticks this into the system is it's pulling a series of sub-agents. So one is a hydrology and a climate agent. So this is trained specifically to go and find that hydrology data and that climate data, look at precipitation, the temporal history of that, and aggregate that relative to the information coming from the remaining agents. So another one, again, document retrieval. So this is pulling any of the design documentation, the facility state agent, which is looking at, okay, what are our sensors doing uh, within the dam, and things like water quality as well too. So there's a number of these agents that are sitting there kind of waiting to be triggered when a query comes in. And what happens is once they fetch that information, they bundle it together and they'll feed back, a quick report, a quick analysis of, hey, what's happening here, right? What's actually going on? And the really, really powerful part about this is what it allows you to do is it allows you to create maps and dashboards essentially on demand specific to your scenario. So if you're asking about, hey, I want to see what my sensors have been doing, what's the context relative to history and historical precedent, then what Trail does is it grabs that information, creates the maps, it creates the dashboards with the sensor data, suited to your needs and confined, with the historical context and the temporal range that's relevant, so that you're not trying to hunt down that data set, that piezometer data set. You're not trying to hunt down all the information as it's scattered across various records. Fundamentally, very important here, I think, is still grounding in what these agents are not going to replace. The system doesn't replace engineering judgment. All it's doing here is it's surfacing the evidence and potential contradictions, if there are any, in the data. It's optimizing the engineer and the site operator's time rather than replacing their judgment on the results. On-site presence, always going to need to have human eyes that are there on site to see what's happening. The thing here is that I think the agent, it allows you as an expert when you go into the field to have a better understanding and perhaps a bit more of a refined idea of where to look, especially if you're dealing with very large sites, right? Things like design accountability. Again, of course, the engineer of record is still the engineer of record. What we're enabling here is, again, faster visibility on how those designs are behaving in reality, and regulatory dialogue as well too. We're building that dossier, but it's still up to humans. It's still up to the experts to make the judgment call on um, what is best for the regulator. All right, so I'll wrap it up there and take any questions. I think tools like this are best played with, or best used in practice. So looking forward to connecting with some folks that are interested in potentially a deeper dive, something maybe a bit more specific to their challenges and problems. And otherwise, happy to take questions at the end of this. All right, thanks again, everybody, and yeah, looking forward to hearing your thoughts.